Hello. I just wanted to give you a quick review of the equations that Dr. Basu gives you. I found that some students find this helpful when preparing for your midterm coming up. So I'm going to do a couple of these videos just to review your equation sheet. Many students find this helpful. Okay, so I'm going to start with the IV bolus since this is the simplest situation that we can have. So, whoopsie, let me just back up. See if I can write here. No, that's not what I want to do. I need to be able to draw. Okay. That's what I need. Sorry about that. Okay. So, this is like the third time I've made this to try to make this work. So hopefully it'll work this time. All right. So with an IV bolus, we're starting with a very simple situation, right? We're giving a dose here, and boom, when we give that dose, it goes into the volume of distribution, and we get our Cmax, right? Our Cmax in this case is equal to our dose divided by volume. We don't have to worry about the drug being eliminated. It just goes in, and that's it. And then it starts to decay at our elimination rate constant rate, okay? And it will fall in a natural log concentration linear way if we have a one compartment linear model. It's our simplest situation, right? So this equation here is what depicts that after concentration 0, we can determine our concentration anywhere along this line as long as we know how much time has elapsed. So what's the difference in time between our Cmax and that any time along that decay curve? And we know that the slope here will be K. So this equation, Cp is equal to Cp0 e to the negative Kt, is a very, 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 very important equation. I equate it with CSS average is equal to bioavailable dose rate over clearance. I call this equation here peanut butter and this one jelly. You have to know these both, like peanut butter and jelly, inside and out, backward and forward. If you know these two equations, you know most kinetics, but you have to know them very well and be able to utilize them. So note that there's two concentrations here, one that happens first and one that happens after that. This equation can only be used for decay, so we can't be getting any drug at this time. It's just it falling off. So after we give a drug, and then how does it get eliminated? I want you to, and then that the resulting equation T time later can be determined. So we've got two concentrations. The difference in time between these two concentrations, right? That's what this T is. And then this, of course, is the slope of our elimination curve, or our elimination rate constant. Now, I want you to know this is not hocus pocus. It's not magic. It's just a rearrangement of our elimination rate constant equation that we know K can be determined by the difference between rise over run, just like what you learned in, I don't know what grade anymore. So the difference between our rise and run, this is going to be a negative number. Our K is not negative, but this is going to be a negative slope because it's falling off, right? So difference C2 minus natural log C2 minus natural log C1 over K2 minus T2, sorry, minus T1, the time difference, right? You all know that equation well. Well, if you like to do algebra, we can simplify this equation or change the equation. Okay, is everybody by that so far? I just brought the denominator over here. And if we can call this change in time t now, note it's the change in time between the 2 points, but we're going to call this t now. And also note that this is equal to the natural log of the difference of C2 divided by C1 there. This is all algebraic rules. Now, if we take the inverse log, natural log of each of these, we take the natural inverse log of ln, that gets rid of those altogether. And this is what we have. If we then isolate our C2 is going to be equal to C1 times e to the negative kt. And guess what? That's the same as this, isn't it? We have our first concentration, and our second concentration is somewhere along here, t time later, and the slope is k. It's just a rearrangement. This is just a rearrangement of our rise over run equation. They are one and the same. I also don't want you to be freaked out by, freaked out by this part of the equation here. All that represents is the fraction of drug remaining at time t. It's just the fraction of drug remaining at time t. So if you multiply that times where you started, that gives you where you're at now, t time later. Okay, so don't get freaked out by this E stuff. I think it freaks people out. I also want you to erase all of this. You don't have to know this. I just want you to realize that this equation is just a rearrangement of that slope equation. How about that erase? The eraser turned off. Eraser turned off again. I don't want you to get freaked out by this equation. Okay? You need to be able to use it and be confident using it. I prefer to think of it like this, that this concentration had to happen before this concentration. And then this is the time difference between these 2 points. This doesn't have to be time 0. But if we're going to write it like this, that this concentration at time t, then it does have to be at time 0 because you have to pin that number somewhere. Okay, now notice this is the same equation, only the CP0 now says dose over volume. Well, we already determined that dose over volume is the CP0 or the Cmax, right? So don't get freaked out about this. I would not give you all this information if it were me. So Dr. Basu is being nice. This is just dose over volume. When it's given as an IV bolus, this is going to be your Cmax, isn't it? This is also not a new equation for you. This equation here, you already know that area under the curve is bioavailable dose over clearance. And remember, and this is the same thing, it needs a little F here though too, bioavailable dose over clearance, right? So I spent a lot of time convincing you, I hope, that elimination rate constant is determined by the clearance and volume of the drug. It's hard to measure clearance. It's not hard to measure K, and it's not hard to measure volume, especially with IV bolus. So we can calculate a clearance by multiplying V times K. That's fine. I just don't want you to think, you know that volume and K do not determine clearance. But if you multiply those together, you can mathematically calculate clearance. You also already knew that total body clearance is equal to renal clearance, hepatic clearance, biliary clearance, what other clearances? Every other organ clearance, okay? Same thing with elimination rate constant. That's a conglomeration of your renal elimination rate constant, your hepatic elimination rate constant, your whatever other organ elimination rate constant. You can just add those up. This is an equation that maybe Dr. Basu uses. I don't usually use it in this course, and it's basically the amount of drug in the urine. It's just a rearrangement, actually, of this equation. specifically for renal clearance. Okay, so now we know the importance and we understand this equation. Okay, this is our peanut butter equation. This is our decay of a one compartment model. Okay, and we can use this in a lot of ways, but you need to understand it really well. Okay, now the next equations that he gives you are concentrations at T time after whatever dose we gave. So what is this piece? Now you have to be able to identify. We just went over this. This is C0 or C max, right? If we give a bolus dose. Dose goes into a volume. This is going to be C max, isn't it? So this is C max or C at time 0, whatever makes you happy. That's what this is. We already know that. We already know this too. What is this? This is just that fraction remaining at time t in the decay. So this is going to be some at time t later, the fraction remaining. So this times this is going to give us concentration at time t. So if we say 2 hours into the infusion, after the end of the or at the end of the bolus, sorry, or 4 hours or whatever time t we give, we can determine that concentration using this times this, right? That's just our peanut butter equation again. But what's this piece stuck in here? What does this mean? 1 minus e to the negative n k tau over 1 minus e to the negative k tau. This is our multiple dosing function. At least that's what I call it. And this is a magic carpet ride to the nth dose. So whatever number you put in here for the number of doses, this is giving several IV boluses time after time, every tau hours. So if we're giving 100 milligrams IV bolus every 8 hours, right? We would put our tau in here of 8 hours. We'd have to know the half-life or the K. If you know the half-life, you know the K. If you know the K, you know the half-life, right? So we'd have to know that. And then however many doses after. So what this is going to do is a magic carpet ride. So if we wanted to know this concentration at time t, we'd put those two pieces together. Let's say it's, again, 4 hours after we give the bolus, okay? So then this t will become 4, won't it? Right? But then let's say we want to fast forward it, magic carpet ride, to the third dose. Well, then we, in here, in this n, we would put 3, right? We need to get to that magic carpet ride 3 doses later, or on the third dose. You just put 3 in there, and then whatever your K and your tau are, this should be on this level. It should be raised to that. And so we know that this is going to be the concentration T time after the dose given on the nth dose. Does that make sense to everybody? So it's just a matter of being able to put the pieces parts together to build your equation. So now if we quickly look at this, CPSS max. So let's say we're at steady state here, and this goes to tau. So if this goes all the way not to time t, but to tau, in this case 8 hours later, that's going to be our min, isn't it? Because we're going to give another dose here. So if this is CPSS max, and if we decay it for tau, this is going to be CPSS min, which you can see is what we had there. CPSS min. You didn't need that equation, did you? And this FR is the same thing as FE that we've been talking about this week in renal clearance, or the fraction of drug excreted by the kidneys or excreted unchanged fraction that's renally, actually FR is probably not a bad way of looking at it. It's renal clearance over total. So it's the percentage of clearance due to the kidneys. Okay. You can also measure it by KR over total K. All right, so that should be it. Now, I just wanted to let you know that we can add any of these pieces parts together with any of these to make these equations. I know you know this equation. This piece of the equation is the multiple dosing function, which is the magic carpet ride to the nth dose, right? Now, if we increase that n, keep increasing that n, this whole part of the equation goes to a 0. And then we'll get 1 over 1 minus e to the negative k tau, right? So this is actually when we give lots and lots of doses, this is our magic carpet ride to steady state. And so that's called your accumulation factor, or I'm not sure what Dr. Basu calls it, but this is just your magic carpet ride to steady state. So if you get your Cmax on your first dose, you can take your magic carpet ride to steady state by multiplying that number times 1 over 1 minus e to the negative k tau. Or you can go to the nth dose, or you can add many of these together. So, oopsie. So let's say you want to determine the third, you determine the concentration. So your patient's going to go to surgery and you want to know the concentration 5 hours after the IV bolus, given on the 4th dose when you're giving 100 milligrams Q8 IV bolus, and your half-life is 3 hours, and your volume is 5 liters. Just making up numbers. Do I have everything I need? We'll probably figure that out, won't we? So we want the concentration 5 hours after. So that's the first thing I'm going to figure out. So what's the concentration 5 hours after? Well, C0 e to the negative kt. So this is going to be 5 hours, right? So that's going to give us 5 hours on the first dose. But then we need to take the magic carpet ride to the 4th dose. So we'll replace that. I'm just going to put the equation in first. N k tau over 1 minus e to the negative k tau. So that's our multiple dosing function to the nth dose. So we're going to replace that n with the 4th dose. Okay. And we want it 5 hours after the bolus is given. So we're drawing a picture. We give the dose, 100 milligrams. We get to our Cmax, and then it falls for 5 hours. So we want to put in our T, we're going to put 5 hours here. How are we going to figure out our C0? Well, our C0 is going to be our dose divided by our volume, which is 5 liters. Our K, like we said, if we have the half-life, we have the K, don't we? So our K is 0.693 divided by 3 hours, right? We put the same number in here. .693 divided by 3. I don't have enough room, do I? 0.3 divided by 3. And then our tau was given to be 12 hours. No, 8. Sorry, 8. Been working on too many problems. Okay, we just plug and chug that out, and that's going to give us our concentration 5 hours after the 4th dose. The trick is being able to understand what all these are, not getting freaked out by it, and just plugging and chugging away. If we wanted to know instead of the 4th dose, we wanted to know at steady state, we would just change this to our accumulation function. That's now going to take us to steady state, 5 hours into this. If we wanted our C min, it would change this to 8 hours. Okay, you got the idea? Hope that helps. Thanks.